what people do.
Yeah.
I'm just trying to see if there are any relationships.
Does that sound like a...
Well, actually, I was thinking before that H infinity might be related to, like, sometimes people design like error correcting codes that it's like guaranteed correction of a certain number of errors. So that kind of reminds me of that. Like, you know, if you have less than 5 errors or something, you know, this thing's guaranteed to correct it.
I
So it kind of reminds me of an H infinity type of thing.
Yeah. It has an H infinity. So it says, if you have less...
Because I thought it was like, you know, H infinity is supposed to get away from like the expected, you know,
Yeah.
anything on the average, and just saying for anything of this, with this character, you know, it'll do something.
Right. Within a certain bound.
Right.
James, what about the thing where, let's just say you have a channel that's, let's say it's just a Gaussian density,
Mm-hmm.
a Gaussian, conditional Gaussian, conditioned on the value you sent.
The channel is a conditional Gaussian?
Yeah.
Okay.
Okay, so let's say you send something from the Gaussian distribution,
Yeah.
and the channel distorts it somehow.
Yeah.
And now I make an estimate of your
Yeah.
signal,
Yeah.
your message.
Uh-huh.
So let's talk scale.
Okay. Yeah.
So I say it's, I think it's 2, you know?
Right.
And then I send the 2 back to you noiselessly.
Right. And then I send the error.
And then you say, well, yeah, you say, well, 2, do you just literally say, take what
X
number you
minus
had
2.
generated and say x minus 2, you know?
I
That's his
might
estimate.
scale it up too.
X minus x half. You
It's
might
possible
scale
I might scale it to make the power, possibly to make the power in every transmission constant or something. Or what do you mean? What would I do? I mean, are you talking about in my scheme, or
Yeah,
just in general? What would I do?
well, you know, in your, let's say, in your scheme, huh?
Oh, in my scheme? In my scheme, it's complicated when you get to continuous channel.
Well, okay, so let's just say you take x minus 2, that's residual.
Yeah, that's kind of similar, but it definitely would not be the same as my scheme. But anyway, let's just take that.
Let's take that, okay, and then if the channel stays the same, in other words, if the variance of the channel stays the same, you're going to have a problem after a while, right? Because you're trying to send a lower and lower magnitude signal, I'm guessing,
Oh, right.
with the same amount of, the SNR.
Right. That's why I might amplify it by something known now.
Okay, so you might amplify it, or equivalently, maybe it's a time varying channel, like at the next time step, maybe the variance halved or something like that,
Yeah.
or something.
Right.
So
I prefer
to keep,
to amplify it.
okay, amplify.
Okay. Yeah. So what's the variance of the second signal? You know, we started off with variance n or p. No, yeah, p. Let's say start off with variance p.
Yeah.
And there's noise power n, noise variance n. So then the variance of the residual is np over p plus n. Is that right?
The variance of the residual. Okay, that's. How do you get that?
Just the standard formula.
Okay, that looks right.
Okay. So then let's say I scale this up to p. Well, what?
All right. Yeah. Okay. Scale up to p.
How do I scale this up to p? So I say this times some constant squared equals p. So I scale it by x. If I scale it by x, then is this right?
Wait a minute. Scale it by x.
Okay, so we had x1, and then we took x1 minus x hat 1.
Yeah. Why are you just looking at me?
Huh?
So we have the variance of x1 minus x hat 1. And then from here I get x1 hat, an estimate, which equals the expected value of x1 given x1 plus w.
Okay, fine. That's a communications.
Okay,
one.
and then in the next step, I take x1 minus x1 hat,
You assume that you can feed back x1 hat perfectly
essentially, yeah. And I send that over,
with more noise.
and I was thinking actually, you know, this might be some kind of, there might be a gain term here,
Okay, sure.
plus w again,
Yeah. You can't get around W,
right.
but you're
And now I
assuming...
have, now let's call this E1. Or let's call the whole thing E1.
All right.
Okay, let's call the whole thing E1.
So there's E0 and then E1. E0 is the first one, and then E1.
Well, there was X1 and now there's E1.
Okay.
And now I'm gonna say E1 hat, again, equals expected value of E1 given E1 plus W, okay?
Okay.
Okay, now, basically E2 equals E1 minus E1 hat.
Okay.
And now I'm claiming that the total error, well, let's say alpha is 1 for now.
Okay.
Um,
Keep in mind, you're trying to get
right, so now
X1.
I'm saying that x1, now I'm saying like my current estimate for x1 is x1 hat, the second one, okay,
Mm-hmm.
equals E1 hat plus x1 hat.
Okay, and you can almost compute X1 hat super 2 up there on the receiving end. On the right.
I can almost compute x1 hat
Right
super
there.
2. Oh, right.
Right there. At that
Oh,
point.
oh, yeah, right, I could do that.
That's where you compute X1 hat, because now you have an updated estimate.
Right.
Now.
So this is where this summation thing comes in. This is where I'm thinking the dynamics play a role or something. But I'm not really sure. I don't quite understand it.
Well, let's expand it. Well, first of all, let's see if X1 hat update super 2 is a better estimate than X1 hat super 1.
Now, it should be, because what I've done is I've sent this signal. You know, it's like if I just decided to make E1 hat 0,
Mm-hmm.
then I would end up with x1 hat, you know? Now if I didn't, now presumably I get some good estimate of E1, which was the error between these two,
Mm-hmm.
and now I can subtract off the error.
Yeah, it seems so weird. It's like you're trying to estimate a quantity with an error, and then you try to estimate that error
Right.
with the same resolution.
Well,
It is.
no, but it's different data, you know, now it's an independent sequence of noise.
Independent sequence of noise. So is it equivalent to just sending X1 again, over and over and over again? Is it any better?
It's better than sending x1 over and over again because this thing has less power. This thing requires less power. That's the only sense in which it's better, I think.
Oh, so for the same power available on the channel, you can,
Yeah.
you multiply it?
What do you mean?
I think first you should convince me that sending sending X1 and then E1
Mm-hmm.
results in better performance than just sending X1 and X1.
For the same power?
Yeah, for the same
Okay,
power.
so let's say that the variance of E1 equals, okay, so I'm going to say the variance of x1 equals p, the variance of w equals n, okay? So using, you know, the standard formula for linear least squares estimation, I believe this is true, but I'm not sure. But the variance of E1 equals Pn over n plus p.
Okay.
Okay, so
And what's,
the variance of x1 would be p.
yeah.
And so this would have to be less than p, so this is less than p. So let's say I could scale this up to p.
That's less than P?
Yeah, because this thing is less than 1.
Okay, good.
Okay, so this is less than p. So I was thinking, well, this alpha, what if I make this alpha so that it scales it up to p? So that we have Pn, n plus p. So the variance of alpha E1 equals this times alpha squared. And now let's suppose I want to make this equal to p. Okay. Then I'll end up with alpha squared equals, cancel out the p's, and we get n plus p over n. So alpha equals this.